How good now?
No, sir, even now it's not visible.
Huh?
It is not visible now, sir. The screen is not being centered.
What is happening?
Now it's visible.
Visible?
Yes, sir. Now it's visible.
Okay now?
Now it's okay.
Huh?
Yeah, it's completely okay. It's visible.
Okay. Should I start then? Uh, yeah. Should I start?
Yes, sir, you must.
Yeah. Okay. So, so the first question is basically regarding to identifying the different angles and different angles associated with the tool in different reference systems. So there are two reference system. How you identify the rake angle, clearance angle, the flank angles like principal cutting edge angle. So these things. So there are two things are like one is called ASA system, which is a machine reference system, and another is called ORS system. It is orthogonal rec system. That is a tool reference system. Are you familiar with this machine reference and tool reference systems?
Yes, sir.
Yeah. So basically, in machine reference system, the coordinates are like means there are reference planes which are identified as pi r, pi x, and pi y. And for tool reference, the reference planes are identified as pi r, reference plane, cutting plane, and orthogonal plane. So here in ASA system, uh, I have given few values. These values, I'm not going into how to convert this ASA to ORS. Have you ever come across this conversion of tool angles? How people do convert this ASA angles to ORS angles? These things.
No, sir. Not yet. No, sir.
A little bit geometry and means math is involved, so this is not the purpose of this course. So I have directly written the matrix manipulation. So here in gamma x gamma y value, so you just need to identify which one is the gamma x gamma y value from this ASA system, and just you need to convert this orthogonal rake and inclination angle. Can you do that?
Yes, sir.
So here basically gamma x is mentioned as 10 degree and gamma y is minus 10 degree. And what about phi? What is phi here? In this conversion
Cutting edge
method,
angle.
huh?
Cutting edge angle.
So phi is basically the principal cutting edge angle. How will you calculate the phi value? Because in ASA system, it does not talk about the principal cutting edge. There is something called end cutting edge, that is phi e, and there is something called side cutting edge. So if you see, let me clear this portion. If you see a cutting tool, this is your end cutting edge angle, this is your side cutting edge angle, and this is your principal cutting edge angle. Now can you calculate the principal cutting edge angle from here? Phi e is given as 15 degree and phi s is given as 30 degree. Okay, so phi s is given, so we can calculate phi from here, right? 60.
From the triangle.
Phi is 60. So if you get the phi value, uh, it's just the matrix multiplication here, right? I'm not getting into this explanation part of how to convert these things because a little bit complicated.
Okay, sir.
Yeah, can you give me a value for gamma naught and lambda? Okay, fine. Means we have come across this how to find out this gamma x, gamma y, phi e, phi s values. And if you know how to convert this ASA to RS system through simple matrix multiplication, you can get the value of orthogonal and inclination angle. And there is same, just a minute, huh? And there is same concept if you want to convert ORS to ASA. So let us move to next question. Okay. So question 2 tells about during turning a mild steel rod at a speed of 0.2 mm, 0.24 mm per revolution. So your S value is 0.24 mm per revolution by a carbide tool having orthogonal rake angle gamma naught equal to 10 degree. Principal cutting edge angle is 30 degree. Chip thickness is found to be 0.48. Determine the value of chip reduction coefficient. Shear angle. Yeah. So your chip thickness value is given. So you need to somehow calculate the uncut chip thickness. And if you can calculate the uncut chip thickness, you can get the value of chip reduction coefficient. And there is some formula for shear angle also. Initially, can you give me a value for chip reduction coefficient? Then maybe I can explain how you can get the value of shear angle. What is A1 here? If I have mentioned these values in the figure. So if this is your phi, is it not A1 equal to S naught sine phi? You concentrate on this figure.
Yes, sir.
So from here, what will be the value of A1? Sine 30 is half 0.12, right? So zeta is 0.48 by 0.12. How much is this? 4. Okay. Now, do you remember what is the equation used for calculating shear angle? Or else I should derive the equation maybe. How about deriving the equation? Just derive the equation. That will be better.
Yes, sir.
So this is your chip coming out. This is your shear angle. You draw some perpendicular to this. Okay, but not perpendicular. Which one is the shear angle? This one, right? What is this angle? So this is your gamma naught, means the rake angle is this. What is this angle? This is gamma naught. This is beta naught. This will be beta naught minus gamma naught. Is it not? Okay. You check it. This should be beta naught minus gamma naught. Now from the geometry, I have already mentioned that which one is the chip thickness, which one is the uncut chip thickness. So your chip thickness is identified by this value, right? AC, right? So what is
equal to
AC?
A2.
Uh-huh.
AC equal to A2.
So AC is basically OA cos beta naught minus gamma naught, right? And AB,
Beta.
for AB, the uncut chip thickness, it is OA sine beta naught. So what is then AC by AB or A2 by A1? It's simply cos beta naught minus gamma naught by sine beta naught, right? Now if you do some manipulation from here, you'll get tan beta equal to, so R is called cutting ratio, which is 1 by zeta. Now can you give me the value of beta? Zeta is 4. How much is this?
Is 0.257.
How much?
Turned out to be 0.257.
0.25. This is tan beta.
So that's that. So it's 14.43 degrees.
How much is the value?
I'm getting as 14.43.
14.43. Okay, I'm taking it as correct. Okay, you got the concepts uh, which I am using here. So basically, there are three things means to relate A2 and A1 to feed and depth of cut. So while you are getting this A2 and A1 value, your chip you can get your chip reduction coefficient. Yeah, by the way, so your chip reduction coefficient can also be calculated through some length of the chip before and after cut, and also can be calculated through cutting velocities, right?
Sir.
So these things you have gone through your video contents. So let's move to the next question. Next question is same thing. Here it tells that there is some feed, there is some depth of cut, and you have some tool geometry provided in ORS system. So whenever you will get this unit now, so in ASA system, this unit is mentioned, this nose radius value. This is always mentioned in inch. In ORS system, this value is mentioned in mm. So whenever this unit is mentioned in mm, you will get that this is ORS system provided. And your coefficient of friction is mentioned as 0.5. Now you need to find out what B1, width of the cut, A1, thickness of chip before and after cut, A1 and A2, and shear angle. So the concept is same. So you can refer this figure, huh? So whenever you are confused within this relation, you can refer this figure. You'll get the relation simply. So your depth of cut is provided, your feed value is provided, your phi is how much? Phi s is provided as 60 degree,
60 degrees, sir.
30. So you'll get A1 value, you'll get B1 value. Uh,
I have no sir.
yeah. For getting a2 value, there is some equation involved. Again, maybe have you come across this equation before? Hmm? Are you there? Yeah. So again,
I have a doubt, sir.
let's not explain this thing. Uh, Again, some complex derivation involved, which is not the purpose of this course. So you please assume that this equation is true, and you calculate the value of zeta from this equation. Your gamma naught value is given as 0 only.
Sir, here phi is equal to 60 degree, no, sir.
What? Phi.
The principal cutting angle, because it is a ORS system and it is directly given.
I think in ASA system, these two are these these angles provided in ASA system. One is called end cutting edge, one is side cutting edge. So
Yes, sir.
they don't talk about this principal cutting edge angle.
So that's for the previous sum.
Right,
You
right.
for the,
So your side cutting edge angle is provided as 60 degree.
here they are directly given in ORS, no, sir, because you explained that in this means it is
Oh,
ORS system.
right, right,
So
right.
it will be
Yeah, thank you, thank you. Correct, 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 correct. Right, right. Here mu is given. Yeah. So I had done this calculation. Can you please confirm? A1 is coming as 0.1732. A2 is coming as 0.554. Zeta is coming as 3.2. And the value of tan beta is coming as 0.325. You have A1 value you have got.
same 0.173.
Yeah. By the way, here this gamma note now, this should be converted to radian when you calculate. Okay, I think you got the flavor, right? Means you got the flavor how
Yeah.
to calculate these things, right?
Yes, sir.
So this question 4 and 5 are coming from the concept of this chip formation mechanism. uh, should I discuss again how the chip forms for ductile and brittle materials and why this build up edge forms? Okay, initially let us
It
do
has
the
been covered, sir.
uh-huh.
Yes, sir. It has been covered. We can brief about it.
Uh, can you get louder a little bit?
It has, it has been covered, sir. We can brief about it.
Right, right. Okay. So, can you tell me which one will give you discontinuous and irregular size and shape of chips? Which material? Among these materials, which one is brittle material?
Brief as
Correct. So, whenever you are having this brittle material, you'll have discontinuous type of chips. Uh, if there is some crack formation, it will propagate very rapidly and it will form some like yeah, it will be kind of discontinuous. Yeah. And for this high speed churning of mild steel jobs with a curved tool having a large positive rake at low feed using a cutting fluid will produce chips of which one is true? So your speed is high, cutting speed is high, you have low feed, rake angle is highly positive,
continuous.
you will end up with continuous type of chip without build up edge. So there are some what should I say? Means you can remember it like this. There is some hard and fast, not rules, but yes, most of the times remember in this way that if you are having, so this is for your future purpose also. So if you are having discontinuous chips, so of course your feed will be higher, rake will be negative, and if you are using, means there will be no cutting fluid to lubricate. If you're having some continuous chips without build-up edge, of course the material will be ductile. Here the material will be brittle, velocity will be high, feed will be low. What about rake? Positive or negative?
Possible and yes.
Yeah. And for with build-up edge, it can be ductile material. Velocity is medium. Feed also, it can be medium or large. This will be absent. So these are some thumb rules to identify whether it will produce discontinuous chip. So continuous chip with build-up edge or without build-up edge. Now this is some calculation from shear strain calculation. Yeah. Do you remember the equation for shear strain? What is y here?
God,
Yeah. If you know the equation, then good. But do you know how is this equation coming from where? So there is something called Spanen's model of card analogy for this ductile material, how the chip is flowing, right? Can you tell me what is why here? This y. So initially your chip was like this. You are having chip like this, like this. But because of some partial sliding up, some shear velocity means some shearing happening, right? For this chip and tool interface, some shearing is happening. So initially your chip was like this, but it displaced to this. Got my point? So what will be del S here? Is this not this PM? This much amount it has slided, right? Initially it was here and this much amount it has slided, this much amount PM. Can you visualize now? So if it is PM, so this is basically Pn plus N. Pn is basically I have drawn a perpendicular from point O, and your initial thickness was Y. Sorry. So that's how it is coming. Okay. As of now, you concentrate on this equation. Let's say we know this equation, and it says that gamma naught is 12 degree. So what will be the value of shear plane angle for minimum possible value of shear strain? So what do you do to calculate the minimum value of shear plane angle?
We can differentiate and then equate to 0. That's what
Right.
happens.
So we'll differentiate with beta and we'll equate with 0. So what will be this? D epsilon by d beta. What is that? Minus cosec square beta. Okay, this is coming a little bit complex. Plus 6 square beta minus. I cannot calculate. Right. So from here, somewhere the sine square beta will cancel, and you'll end up some tan betas equal to something. I think so. Maybe tan square beta. What? Uh, Sin A minus B sin A cos B. Yeah, I think you will end up with some tan square beta value, and from there you can calculate beta.
Yes, sir.
Right? Is it okay?
Sir. Yes, sir.
Now in question 7, this is from merchant circle diagram. It says that you are having a turning tool of orthogonal rake 0 degree and principal cutting edge angle 90 degree. Oh, principal cutting edge angle is 90 degree. So the tool will look like this. This is the first point. This is okay. Tool will look like this. Now, some values are given. Pz equal to 800 and px is 400. You need to calculate mu that is occurred at chip tool interface under the above mentioned conditions. Are the abbreviations are getting difficult to adapt? Means this pz, pxy. Are you familiar with this abbreviation or something else? I mean the nomenclature.
So one would be tangential, I guess.
Sorry.
Those are components, tangential and
Right. Yeah. How will you calculate this pxy or this tangential thing? So whenever you visualize this single point cutting tool, there is always a cutting force, which I have mentioned it here. This can be resolved in three components: px, py, and the main cutting force. So pz is basically your the largest in magnitude, right? What can you say about px and py from this figure? You can refer this figure.
five.
Am I right? So from here you can calculate pxy. Phi value is given. Px value is given. So it's basically px equal to pxy, right?
Py equal to 0.
Px equal to pxy sin phi. Phi is 90. So pxy, this one will be 400
Yes.
Newton only. Now you have given this, uh, your gamma naught value is 0 degree. So how does this merchant circle diagram will look like if your gamma naught value is 0 degree? There is no gamma naught. So these four will not form a rectangle. Are you getting my point?
Yes,
If
sir. Yeah.
there is no gamma naught, so this angle is also 0. If gamma naught is 0, so this is also 0. So this will simply form a rectangle. This one, right? So what can you say about n? So you have
Equal to P, sir.
right. So your f equal to pxy equal to 400, n equal to pz equal to 800. So you can simply calculate mu equal to f by n. Okay, let's move to next question. It tells about you have dia of 150, rpm of 560. And tip to cut is 4 mm. It's given pz equal to 1000, py equal to 200, chip thickness is 0.8. What is tau and sigma? I mean, in the shear plane, what will be the shear and normal stress? What will be the shear stress? Right? PS is your shear force. And if this is your shear plane, so say that is a AS. And how will you calculate this AS? This into this. What is this length? If this is A1, this is A1 by sine beta naught into B1, right? And your A1 is S naught sine phi, B1 is T by sine phi. So it's basically give you this value. Depth of cut into feet divided by sine beta naught. Now you need to calculate beta naught, right? We have gone through this equation before. And how much is your orthogonal rake angle is given. Yeah. So your orthogonal rake is given as how much? How much is the orthogonal rake?
Minus 12 degrees.
Minus 12. Right? Now your A2 value is given. Uh, Yeah, A2 value is given. You know your S naught. S naught is basically the feed, and you know the phi also, that is 60. So this is also known. So from here we can calculate beta naught, right?
Yes.
Say this is some value. I don't know what is the value. So if you know the beta value, so from here can we calculate the shear force from merchant circle? Here PS. So you have given some PZ and PXY value. Sorry, PY value. From PY you can calculate PXY. So we can write PS in terms of PS in terms of PZ and PXY, right?
Yeah.
So if I refer the equation, it's like PZ. This will come from merchant circle diagram. So now you know your shear force. You know your what is the shear area, right? Initially we had calculated AS, right? What about the normal stress? It's the normal component. So this component Pn. So you can convert this Pn, means you can calculate Pn also in terms of Pz and Pxy.
In space and sign beta plus cos beta.
Right? Understood?
Yes, sir.
Uh, I accidentally, maybe this is the same question. Yeah. Okay. So one thing is determine the coefficient of friction also. So it's basically mu equal to F by N. Same you can calculate merchant circle diagram. Means this value F and N in terms of PZ and PXY. This we can find out it simply, right?
Yes, sir. Yes, sir. Yes, that.
This is my last question. So it says about under a given condition of turning, the tool life was found to decrease from 24 minutes to 16 minutes when only the cutting velocity Vc was raised from this to this. So your T1 is given as 24 minute, V1 is given as 200 meter per minute, T2 is given as 16 minute, V2 is given as 250 meter per minute, and you have to calculate T3 when your V3 is given as, right? How will you calculate? You know Taylor's tool life equation. So if you equate these two equation, you will get the value of n, right?
Yes, sir.
Then you simply either v1 t1 to the power n or v2 t2 to the power n is equal to v3 t3 to the power n,
B3, T3. Yes, sir.
right? So you got all the concepts? Any confusion anywhere? All okay?
Got it, sir.
Okay. Should I end here now? Sure.